So, um, I think we have this tendency to look at, a towering 19th century Victorian brick home or a massive historic courthouse, and we just see this absolute unyielding permanence.
Right. Yeah. It's brick. It's heavy mortar, so we just assume it's going to outlast us all.
Exactly.
Yeah.
But today's deep dive actually reveals that this feeling of structural permanence is, well, it's entirely an illusion.
Completely.
Because there is this relentless microscopic war happening right above our heads, like
Yeah.
inside the very materials we assume are basically indestructible.
Yeah. And we connect this to the bigger picture. Exterior home maintenance is really this ongoing high-stakes negotiation with nature.
Right.
When you look at the underlying physics and the chemistry of masonry, those roof lines aren't static monuments at all. They are highly active environments.
Constant movement.
Exactly. They're constantly reacting to temperature, to moisture, chemical stresses. And, in coastal environments especially, nature is driving a remarkably hard bargain.
Okay, let's unpack this, because today we are digging into the specific methodologies of John Constantine and his team at Portland Chimney Service.
Yeah, operating out of Maine, which is quite the environment.
Right. It essentially serves as this extreme stress test for architecture. And they put out this brilliant series of guides and operational posts earlier this year, so between February and May 2026.
Really detailed stuff.
Very. Breaking down exactly how masonry survives. So our mission today is to explore the physics of that brickwork, the actual thermodynamics of chimney fires, and what it really takes to bulletproof a home against brutal weather.
And, even if you don't live in a coastal blizzard zone, understanding how a structure breathes and fails and ultimately survives, it's going to change how you look at every brick building on your street.
Totally. So starting with the environment, the climate of Casco Bay in Portland is kind of an ideal laboratory for understanding these failures, right?
Oh, absolutely. I mean, you have freezing coastal gales, driving rain that moves completely sideways, and an atmosphere that's just loaded with highly corrosive salt air blowing directly off the Atlantic Ocean.
Just a brutal combination.
It really is. And to understand how this destroys a structure, we basically have to rethink what a brick actually is.
Right, because we perceive it as a solid barrier.
Exactly. But it's inherently porous. It basically acts as a hard sponge. A single standard brick can actually absorb up to 1.5 cups of water.
Wait, 1.5 cups per brick?
Per brick, yeah.
Oh, wow. So when you multiply that by the thousands of bricks making up a single chimney stack, I mean, you are talking about gallons and gallons of water suspended directly inside the architecture of the house.
Yeah, it's a massive amount of water. And what's fascinating here is the sheer disparity in the physics once the temperature drops.
Because it freezes.
Right. We all know water expands when it freezes, increasing its volume by roughly 9%. But it's the hydraulic pressure generated by that expansion that does the real damage.
How much pressure are we talking about?
Confined freezing water can exert tens of thousands of pounds of pressure per square inch.
Tens of thousands.
Yeah. And a typical historic kiln-fired brick has a tensile strength of maybe a few hundred psi.
Oh, so the math is completely asymmetrical.
Completely. The ice pushes outward from within the pore structure, and the face of the brick simply pops off. In masonry, this structural failure is called spalling.
Spalling. Okay, so a brick is essentially a hardened sponge soaking up the Casco Bay fog until winter turns that water into microscopic ice daggers.
That's a great way to put it. Microscopic ice daggers, yeah.
And it seems like the most dangerous part of spalling is how quiet it is. I mean, you don't hear a loud crash when the face of a brick gives way.
No, you don't. It's totally silent.
So property owners probably usually miss this slow deterioration entirely, right?
Usually, yeah. At least until the structural integrity is so compromised that the chimney starts visibly leaning, or, dark water stains suddenly blossom across their living room ceiling.
Yikes. And then there's the salt factor too, right? Because of the coast.
Yes, the destruction is compounded exponentially by the coastal location. The salt air introduces this secondary mechanism of internal decay.
How does that work?
Well, deliquescent salts from the ocean spray penetrate the porous brickwork in solution, basically riding in with the moisture.
Okay.
Then, when the weather clears and the brick begins to dry out, the water evaporates, but the salt remains behind.
Oh, I see.
Yeah, and it forms crystals inside the microscopic pores of the clay.
So the crystallization process itself is exerting pressure from the inside. just like the ice does in the winter.
Exactly. The growth of those salt crystals exerts massive expansive forces, which is a process known as subfluorescence.
Subfluorescence.
Right. It basically pulverizes the masonry from the inside out. So you have the freeze-thaw cycle destroying the brick in the dead of winter, and salt crystallization destroying it during the dry days of summer.
It's just getting attacked year-round.
Yeah, this continuous cyclical abuse is an equal opportunity destroyer. It affects 19th century Victorians in Portland's West End and mid-century capes in Deering Center alike.
That makes sense. And once that 9% expansion blows the face off the brick, water basically has a superhighway directly into the home.
It does.
So to stop it, I mean, you can't just slap caulk on the surface, right? Yeah. You have to reset the entire structural baseline through tuck pointing, which is funny because I always assumed tuck pointing was primarily cosmetic.
Oh, a lot of people do.
Yeah, like just smearing new mortar over the cracks to make the joints look clean again.
Right, but cosmetic patching over a failing joint is structurally useless. Tuck pointing is actually a highly specialized structural intervention.
So how do they actually do it?
Well, professional crews use diamond-tipped grinders to route out the failing mortar joints to a very specific depth, usually about 3/4 of an inch.
Okay, wow. 3/4 of an inch is deep.
Yeah, it removes the degraded material and creates a clean, solid channel. And only then do they pack fresh mortar into those joints to restore the structural integrity of the wall.
Now, here's where it gets really interesting, especially for anyone living in an older home. You cannot just run to a hardware store and buy a bag of modern Portland cement to tuck point a historic chimney.
No, absolutely not. That's a disaster waiting to happen.
Right, because there are strict historic New England guidelines that dictate the exact chemical makeup of the mortar you use.
Yes, there are.
Because old bricks, like those forged in the 1890s, they were fired at lower temperatures, making them significantly softer, right?
Yeah.
They're designed to flex, and they're designed to breathe.
Exactly. And modern Portland cement cures through a chemical hydration process that results in incredibly high compressive strength and extremely low vapor permeability.
So it doesn't breathe at all.
Right. It is rigid and unforgiving. Pre-1900s mortar, on the other hand, was primarily composed of lime and sand. Yeah, and it cures through carbonation by absorbing CO2 from the air. So this historic lime mortar remains relatively soft and highly vapor permeable.
So what happens if you mix them?
Well, if you place rigid, modern Portland cement between soft, historic bricks, you alter the entire functional dynamic of the wall.
Because the moisture is going to find the path of least resistance.
Precisely.
If the mortar is too hard to let the water vapor pass through, the moisture gets forced directly into the soft historic brick instead.
Yeah.
Then the winter hits, the trapped water freezes, and the brick just shatters.
Exactly. What's crucial to understand is that mortar is actually engineered to be the deliberate weak point in a masonry structure.
Wait, really? It's supposed to be the weak point?
Yes. It is designed to be sacrificial. It's supposed to absorb the structural shifts, the thermal expansion, the weather impacts degrading slowly over decades to save the harder bricks from cracking.
Oh, that makes so much sense.
Right. Understanding this delicate balance of compressive strength and vapor permeability is the fundamental difference between true historical preservation and a cheap patch job from a big box store that will destroy the chimney in a single winter.
But sometimes, I mean, the decay is so advanced that grinding out joints just isn't enough, right?
Unfortunately, yeah.
Like when a concrete crown is completely compromised or the stack is visibly leaning, the structural baseline is just gone. So the approach has to shift from tuck pointing to, and I love this phrase, from the source surgical deconstruction.
Yeah, it's a great term because it's not just demolition.
Right. Demolition sounds like a chaotic wrecking ball situation. But this is precise. Crews erect secure staging, they protect the surrounding roofline, remove the flashing, and dismantle the failing sack brick by brick down to a solid, healthy baseline.
Exactly. They remove the liability before gravity does it for them catastrophically.
Right. But rebuilding that exterior shell with historically accurate, breathable mortar is only half the battle, right?
Right. Oh, definitely. The transition from exterior weather defense to internal chemical defense is vital.
Because a structurally immaculate exterior is completely irrelevant if the internal flue is a fire hazard.
Exactly. Burning wood is a really complex thermodynamic process. And when that process is inefficient, it creates a highly dangerous combustible byproduct called creosote.
Yeah, and we tend to think of smoke as just hot air, but it's actually full of vaporized unburned oils from the wood.
That's right.
So when a fire isn't burning hot enough, That smoke cools as it travels up the chimney. Once the temperature of the flue gas drops below about 250 degrees Fahrenheit, those vaporized oils condense against the cold terracotta tiles near the top of the stack.
Yeah, it's literally raining liquid tar down the inside of the flue.
That is terrifying.
It really is. And that condensation tracks the life cycle of creosote, which develops in 3 distinct phases.
Okay, walk me through those phases.
Well, stage 1 is a relatively benign velvety soot that can be brushed away easily.
Standard sweeping.
Right. But if left unchecked, the continuous condensation and heating cycles bake that soot into stage 2, which is a highly porous, crunchy, kind of flaky crust.
And stage 3 is the nightmare scenario.
Yeah.
It transforms into a hard, glazed, highly explosive tar. Is this third stage creosote basically like burnt caramel, coating the inside of your chimney just waiting for a spark?
Yes, that is exactly what it's like. It looks like black, burnt caramel, and it is incredibly stubborn and highly reactive.
So you can't just scrape it off yourself.
No, a homeowner armed with a wire brush cannot break the bond of third-stage creosote glaze. It requires professional intervention.
Like what?
Using high-speed rotary chains and heavy chemical modifiers to actually alter the molecular structure of the tar so it can be safely removed.
Wow. And the Chimney Safety Institute of America, the CSIA, they report that just 1/8 of an inch of creosote buildup is enough to ignite a devastating flue fire.
1/8 of an inch. That's nothing.
Right. A homeowner could easily have that much buildup hidden near the top of the chimney and never see it from the living room hearth.
This raises an important question, though. How often do you evaluate the internal lungs of your home?
Yet,
Because a dramatic, explosive chimney fire isn't the only hazard here. The internal environment of a flue is subject to immense thermal shock.
from the heat of the fire.
Exactly. You have 400-degree exhaust gases hitting freezing terracotta clay tiles. Over time, those clay liners just crack and shatter. Metal dampers rust out from water pooling on the smoke shelf.
And the EPA Burnwise program highlights a really critical side effect of those structural failures.
Yes, they do.
A damaged, cracked flue significantly decreases the draft efficiency of the chimney. So instead of the system functioning like a powerful vacuum, pulling the toxic exhaust up and out of the house, a compromised flue actually pushes carbon monoxide-heavy particulates back down into your living space.
Right.
So the family might not face a sudden fire, but they are breathing compromised air all winter.
Which is incredibly dangerous. And the reality is the traditional terracotta clay liners that were standard in home construction for decades, they simply cannot withstand modern moisture challenges and continuous freeze-thaw cycles without degrading.
Oh, what's the fix?
The definitive structural solution is upgrading a failing clay system to a continuous insulated stainless steel liner.
Ah, stainless steel.
Yeah. Stainless steel is entirely impervious to the freeze-thaw cycle. It does not shatter under thermal shock, and the smooth, cylindrical design significantly improves the draft efficiency of the fireplace.
That makes total sense. Okay, so let's track the progress here.
Sure.
We armor-plated the outside by grinding out the mortar and replacing it with historically accurate line putty.
Right.
We've upgraded the internal flue with a stainless steel liner and scoured out the explosive third-stage creosote.
Yep.
So the final critical phase is implementing a holistic shield to protect this massive investment. And that requires waterproofing the exterior.
Yes. Waterproofing is the final line of defense. But, and this is huge, applying standard paint or a hardware store clear coat to a brick chimney is a fatal error.
Because it traps the moisture.
Exactly. Film-forming sealants trap the internal moisture inside the masonry because we know the brick is already holding gallons of water like a sponge.
Right, the 1.5 cups per break.
Exactly. Sealing it guarantees that the trapped moisture will freeze, expand by 9%, and just shatter the brick from within.
Wow, so trying to protect it with the wrong stuff actually destroys it faster.
Absolutely. The methodology relies on professional-grade, vapor-permeable silane and siloxane treatments.
The silane and siloxane.
Yeah. Instead of forming a film on the surface, these molecules penetrate the brick and line the microscopic pores.
So they act exactly like a Gore-Tex jacket for the masonry.
That's a perfect analogy, yeah.
Because they allow water vapor, which has a very small molecular size, to breathe out and evaporate, while simultaneously acting as a hydrophobic shield to stop driving liquid coastal rain from pushing in.
It operates as a highly effective one-way valve for moisture management.
Brilliant. And controlling the points of moisture ingress also requires addressing the very top of the system, right?
Hmm.
Like chimney caps.
Oh, chimney caps are essential. A single missing chimney cap allows gallons of rain and snow to pour directly down into the interior of the house.
And animals too, right?
Yeah, spring nesting animals. The National Fire Protection Association actually mandates annual inspections specifically to identify these hidden water issues because an uncapped flue is just an open invitation to severe internal water damage and blocked exhaust paths.
Okay, so this brings me to a details from the guys that I really wanted to ask about. The gutter connection.
Ah, yes.
Because I always thought of the roof, the gutters, and the chimney as three completely separate independent systems on a house.
A lot of people do.
Wait, so why can't I just have my gutter guy scoop the leaves and my chimney guy check the flue? Why do they need to be integrated? If my chimney is failing, it feels counterintuitive to look at the gutter alignment.
Well, here's the thing. Water operates systemically. It does not respect the arbitrary boundaries of the different contractors you hire.
That's a good point.
The wind and rain dynamics of a severe storm functionally link these systems together. If a gutter is clogged with debris or misaligned, the water overtops the channel.
And spills over.
Exactly. And if that overflow cascades continuously down onto the chimney chase or splashes violently against the base of the masonry, the brick acts exactly as it is designed to.
It absorbs it.
It absorbs it, yeah.
And because it's a constant cascade, the brick never gets a chance to dry out. The Gore-Tex waterproofing treatment can handle driving rain, but it cannot handle a continuous waterfall from a clogged gutter.
Exactly. That volume of water overwhelms the permeability of the masonry. This disconnect in exterior maintenance leads directly to rotted fascia boards near the chimney integration and severe accelerated spalling at the base of the stack.
So they really are connected.
You simply cannot protect the chimney without ensuring the water management system of the entire roof is functioning correctly. It requires a holistic, integrated defense strategy.
Man, so what does this all mean? It means that home maintenance, especially when you are dealing with aggressive, unforgiving climates like Portland, Maine, is never just a disconnected checklist of chores.
No, not at all.
You don't just fix a chimney and walk away. Protecting a home requires understanding the physics of the environment.
Absolutely.
From diamond grinding soft 1890s mortar so the house can properly exhale moisture, to installing stainless steel liners to prevent carbon monoxide blowback, to applying vapor-permeable Gore-Tex sealants. I mean, it requires a proactive, deeply specialized defense strategy before winter hits.
It really does.
When you look at how John Constantine and the crews at Portland Chimney Service actually execute this on the ground, you realize why their hotline, 207-835-3683, is probably on speed dial for half the historic homes in the Maine coast.
Yeah, I would imagine so. And for you listening right now, the real value of this deep dive is applying this perspective to your own surroundings.
Exactly.
Whether you own a historic Victorian on the coast, a mid-century home in the suburbs, or even a brand new architectural build, look up at your roofline differently today.
Yeah, look for the clues.
Pay attention to the subtle physical signs. Is the mortar receding deeper than the brick? Are there dark, damp stains on the exterior? Understanding the mechanisms of thermal and chemical decay is really the necessary first step in preserving the place you call home.
It fundamentally changes your perspective on the built environment around you.
It reveals the hidden life of architecture. And I want to leave you with a final thought to chew on, something that builds directly on the physics we've uncovered today.
Let's hear it.
We learned that old 1890s brick and mortar was specifically designed to be soft. It was engineered to flex, to absorb microscopic movement, and most importantly, to breathe moisture out. That intentional structural imperfection, that flexibility, is exactly why those historical structures have survived for well over a century when they are maintained with the right materials.
Yeah.
But today, modern construction relies heavily on rigid, highly engineered, and totally sealed synthetic materials. We seal our houses up as tightly as possible to achieve perfect energy efficiency.
That's true. Everything is airtight now.
Right. So the question becomes, given our modern obsession with sealing everything off entirely from the elements, how will our highly engineered airtight modern homes actually fare in 130 years compared to those old, breathing Victorian chimneys standing tall on the coast?
Wow, that is a really fascinating point, something to think about. But the next time you look at a massive historic brick building, you'll know the truth. It isn't invincible, and it isn't solid stone. It is alive, it is breathing, and it is fighting a microscopic war every single day.